Okay, this is one of my favorite equilibrium problems. Couple reasons. First reason is I love the fact that there's a solid in here because one of the things I hammer on is pure liquids and solids do not enter into equilibrium. Solid carbon and carbon dioxide gas at 1,160 K were placed in a rigid 2-liter container, and the reaction above, represented above, occurs. As the reaction proceeded, the total pressure in the container was monitored. When equilibrium was reached, there was still some CS solid carbon remaining in the container. Results are recorded in the table below. The other thing I like about this problem is when does it reach equilibrium? They'll ask you that. And remember, equilibrium occurs when there's no net change in the container, or there's no net change. So right here, we're sure that because 8.37, probably it should put 12, 8.37. We know that at 8 hours, it was at equilibrium because the equilibrium pressure is 8.37. Okay, and so as this reaction proceeds, the pressure changes, and then all of a sudden it stabilizes. And so I like that. I like that about that problem. Write the expression for the equilibrium constant. So let me just do this again. Holy mackerel, I have no idea what I just did there. So what happens is we have solid carbon, which isn't used, plus CO2 gas goes to 2CO gas. I can see it's balanced, one carbon, which is 2, 2, and then no oxygen, 2 oxygen, 2 oxygen. And they want Kp, so that means we're supposed to use pressures, not concentrations. Also, it's the pressure of the carbon monoxide gas squared over the pressure of the carbon dioxide gas. And this is an implied one. You don't have to put it there. Calculate the number of moles of CO2 initially placed in the container. And so this is the most important gas law equation, and N is the number of moles. So N equals PV over RT. The only thing that's kind of tricky here, if we go back, is initially means at time 0. So the total pressure in the container at time 0 is 5. And in the beginning, it's solid carbon and carbon dioxide. That's what happens in the beginning. So it's 100% this, 0% this. And then it goes until equilibrium is reached. And so remember, the initial pressure is 5 atmospheres. You get that off the table. And so the initial pressure is 5 atmospheres. So that's P. If you go back to the beginning, and keep flipping back and forth, this is the volume right here, 2 liters, and then 1,160 K is the temperature. And so this is, the volume is 2 liters. And then R, and by the way, if it bugs you that there's not stuff down here, R is downstairs, so I'm going to do the reciprocal 0.08206. Let me say it again. I keep saying these as I'm taping these. In 2008, the value for R was 0.0821. With the new test guidelines, they just added a sig fig. And so it's going to, if you're looking at the online scoring guidelines, it's going to affect the answer per mole K. And so what happens is atmospheres cancels with atmospheres and liters cancels with liters. And the temperature is downstairs. And so I'm going to do the reciprocal of that. So it's 1 over, I hate this when this stuff happens when I'm recording. I'm sorry. It's going to be 1 over 1160K because it's downstairs. And you notice we're solving for number of moles, and that's the only thing that hasn't canceled. And this has 3, and this has 3, and this has 1, 2, 3, 4, and this has 4, and so we only get 3. And if you do that on your calculator, you should get 0.105 atmospheres. Fabulous. Okay. Next one, for the mixture at equilibrium at 1,160 The partial pressure of the CO2 is 1.63 atmospheres. Calculate the partial pressure of the CO. I did this very different than the scoring guidelines, and I just want to talk about um, why I like my way better. I don't really care when you take your final which way you do. Okay, so now remember, um, I'm going to set up an ice chart, and this is a capital I, capital C. And because this problem is about Kp, not Kc, you need to put atmospheres here. If it's a Kc problem, these are capital M's for molarity or moles per liter. And again, solids do not participate. In the beginning, we know that this is 5 atmospheres. I stands for initial. And we know in the beginning there's none of this. And then now this is interesting. The partial pressure at equilibrium means we're in the E row. The partial pressure of the CO2 is 1.63 atmospheres. And then they want you to calculate this. Now, here's what I like it. This has to be negative 3.37, because remember, you always get the E row by adding these. This has to be negative 3.37. If this is negative 3.37, this has to be positive 2, because of the 1 to 2 mole ratio, times 3.37. Because of the 1 to 2 mole ratio, this side goes down, this side goes up. You're used to writing x and 2x. But the thing that's interesting is we know what x is. X is 3.37. And when you do 2 times 3.37, so 3.37 times 2, 14 carry the 1, 7 carry nothing, 6. And so this is 6.74 atmospheres. Now, interesting, what would the total gas pressure be at equilibrium? 1.63 plus 6.74. If you add them together, you get 7, and then carry nothing. 6 and 7 is 3, carry the 1, and then 8.37. But if you go back to this chart, this makes perfect sense. What is the equilibrium gas pressure? 8.37. Now, the reason I like my way better is because it uses this 1 to 2 mole ratio, and it's how ice charts you normally do it. What they do on the scoring guidelines, which is actually a much easier process and probably a little easier, 1.63, that's the pressure of the CO2, plus X, the pressure of the carbon dioxide, has to equal 8.37. Obviously, the total pressure is a sum. And either way, the answer to this problem is 6.74 atmospheres. I just like my way better because it uses the way that we teach you ice charts. What's the value of the equilibrium constant? Well, we take the answer previously, which is the pressure of this carbon monoxide squared over the pressure of the carbon dioxide. And we just figured out that the pressure of the at equilibrium, this is 6.74, and then this is 1.63. And when you do that on your calculator, you get 27.9. So the equilibrium constant is 27.9. Again, let me just point out, if this answer is wrong in part 1, but you use it right in part 2, you use the wrong answer correctly, you don't lose points again. They're very nice. Okay, if a suitable solid catalyst were placed in the reaction vessel, would the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure of the gases at equilibrium without a catalyst? Justify your answer. Okay, hammering on this. Remember, you always answered the question first. And so the pressure would... Okay, so how do I want to write this? Sorry, I don't like the way I worded that. So what happens is, let me just get this. The pressure isn't going to change, because I need to tell you that I've probably said this 1,000 times. I haven't taught you guys yet. It's summertime, but normally I say this 1,000 times. A catalyst does not affect equilibrium. All a catalyst does is make the reaction get to equilibrium faster. It doesn't change any of the numbers in the problem. It does not affect the position of the equilibrium. So you would say first, always answer the question first. Uh, the pressure, um, the total, here we go again. I'm really struggling right now, guys. I'm sorry. Um, I should have just thought about this more before I jumped in. I would just say the final total gas pressure at equilibrium without a catalyst would, now this emphasis is mine, equal the final total gas pressure at equilibrium with a catalyst. Now it says justify your answer, and here's the justification. A catalyst speeds up the reaction, but it does not affect the equilibrium position. Now, I don't know if I've talked about this term all that much about equilibrium position, but it's the idea of position, because we talk about equilibrium shifting left and equilibrium shifting right, and that's a position. Left and right are positions. And so if you add a catalyst, it just makes it get to equilibrium faster. So like for instance, if I go back here, maybe this would be 1 hour, 2 hour, 3 hour, 4 hour, 5 hour, that it would get to equilibrium twice as fast, but it wouldn't affect the pressure at equilibrium. Okay, this one's interesting. In another experiment involving the same reaction, we still have a 2-liter flask. We have 10 grams plus CO and CO2. So now interesting, we have this equation, we have this reaction going, but it's different in that when we did our first ice chart, this is interesting. Okay, and they give you 10 grams of this. Who cares? Doesn't affect. Here's the deal. They're telling you that initially this is 2 atmospheres and this is 2 atmospheres. And the question is, well, these are, it's easy when this is 2 atmospheres and this is 0, because you can only go up from 0. But which way is the partial pressure of the CO2 going to increase, decrease, or remain the same as it approaches equilibrium? So I'm just telling you the background. This is what you do. You calculate Q, which is called the reaction quotient. This is what you call K when you're not at equilibrium. You're at initial. And we know that this is the equation for both Q and K. And so here's the deal. This is 2 squared, and this is 2. I could do this without a calculator. 4 divided by 2 is 2. Now the reaction quotient is 2, which is, so do that first. So what you do with reaction quotient is you don't put in the equilibrium conditions, because if you're using the equilibrium numbers, it's not called Q, it's called K. You put in the initial conditions, and it's 2. And what you need to know is 2 is smaller than 27.9. We figured out back here that the equilibrium constant was 27.9 for this problem. Remember, equilibrium constant is a constant provided you don't change the temperature, and the temperature is the same. And so what happens is this problem is, well, as this reaction proceeds, the 2 will grow until So the 2 needs to grow until it hits 27.9. Now remember, equilibrium constant is right over left. And the only way that this can grow is if the right side gets bigger, because when the number in the numerator gets bigger, Q gets bigger, or the left side gets smaller, because if you divide by a smaller number, the answer gets bigger. Either one of these things makes this grow. Well, if the right side is getting bigger and the left side is getting smaller, let's just look. I mean, you answer the question. The right side needs to get bigger. The left side needs to get smaller. The right side's going to get bigger. The left side's going to get smaller. CO2 is on the left. So the partial pressure of CO2 will decrease. Now, I'm getting ready to answer the question. I'm actually had to do all of that before I could answer. So let me extend the page. Let me switch colors, because on the AP exam, they want you to answer the question first. The partial pressure of CO2 gas will decrease. Always answer the question in the first sentence. And then your justification is Q equals 2. KP equals 27.9. So the pressures on right. And let's just say this, because this will match your book. Sorry. So reaction will proceed to the right. It's going to shift right, but we don't want to talk about equilibrium shift because we're not at equilibrium. It will proceed to the right, which is how you say shifts right when you're not at equilibrium, because you need to get more stuff on the right and less stuff on the left. So CO2 gas pressure will decrease. And this part you don't need to have, but I'm just putting this here to help you understand this. And the CO2 gas pressure will increase as the system approaches equilibrium. And that's it.